All right, so what, if we look at this first question, 23, what is the science physical property that's being used here to determine the volume of the rock? Volume and density are related to one another. And the fact that the rock sinks kind of is a necessity, I think, here. But when this rock sinks to the bottom and the water is pushed away from it, right? And then we see, that water is pushed up against the glass in all directions, but then we see, because there's no top, that water rises, correct? Okay. What is that? When you get into a swimming pool or a bathtub and the water moves, okay, or maybe, when you walk into this room or you walk by someone and there's a slight breeze because of your walking, why is that? What's going on? Okay, things are being pushed, right? Okay, because two objects cannot do what with one another? Or two objects cannot at the same time occupy the same exact space, correct? Does that make sense? Okay. That idea, that concept, so if Gage and I want to occupy the same space, one of us is going to have to move the other, right? Okay. And because Gage has that very strong odor, I would probably be the one moving. So that movement, when something is moved away or pushed away, it's referred to as displacement. Okay? And we are, one of the things that we do in the physics class and in advanced math and trigonometry class is deal a lot with displacement in regards to the direction that the displacement occurs. Okay? Displacement happens a lot just in other areas, other kind of mathematical and science arenas. But this one's talking about water displacement. Okay? And something is going to produce, the act of putting that rock in the water is going to produce a new volume. Okay? And that new volume is going to be different than the volume of what we started with. Does that kind of make sense? The only thing that is going to be accountable for that new volume or that different volume is the rock. Okay. So if I do this try to find a volume of the liquid, I'm not interested in finding the volume of this kind of aquarium that I've got up there, right? I'm interested in finding just the amount of water, the volume of water. Okay. It's just nice for displacement purposes that this is in a structured, confined aquarium. Okay. Maybe in a science class you use a graduated cylinder, right? Okay. Can I find the volume of this prism pretty easily? Volume of the prism. Okay. Now I'm talking about the liquid prism, the water. Okay. It's 30 by 45 by 20, isn't it? Okay. Obviously the aquarium is a little bit taller than that, but this 20 is telling me the height of the water. So I have 30 times 45 times 20. Okay. When I multiply that out, it's 27,000 cubic centimeters. Okay. Now here's something we should think about. It's 27,000 cubic centimeters inside that aquarium. If I pour that out on the floor and it creates a big puddle, how much volume is in that puddle? 27,000 cubic centimeters, right? Cannot destroy matter, right? Okay. So that volume is going to be the same whether it's in that rectangular prism shape or if it's free flowing somewhere on the floor of the puddle. Okay. But to do displacement, we want to confine it inside that prism, inside that aquarium. So I then put this rock in. And when I put that rock in, this number changes to what? 20.5. So the new volume is L times W times H. It's 30 times 45 times 20.5. If I multiply that out, I get that number, right? What's the difference between those two numbers? 675. What is the only object that could account for that difference? The rock. Okay? So the rock is having or has a volume of 675 cubic. Yes. Yes. That'll work. That's not the, I mean, a word, I don't know if that's the, because now, and it's fine, so the argument then, the assumption then is that the rock, I think about it, you're saying the rock is going to be not so much an irregular shape, but it's a prism itself, which would be fine, yes, that'll work. So if you would take that rock and maybe, if it's an irregular rock or whatever, grind it up, make like a cement slab out of it with a base of 30, a length of 45, and a height of 25 centimeters. It'd be the same exact volume as the irregular rock. Yes, that works. And that's something, guys, that we do a lot with trying to measure volumes of irregular shapes. Okay, and even regular shapes. It doesn't really matter. But if I've got some object that I want to figure out the volume for, the quickest, most efficient way is to see what kind of fluid or some type of fluid that displaces, okay, and see that rise or that difference in volumes of the fluid that gets displaced. And it doesn't have to be water, okay? A lot of times we're interested in a gas being displaced, okay? And that's why I said when you walk by somebody and there's kind of a wind, right? Kind of a breeze, okay? Because you're displacing, as you walk, you're displacing those air particles, right? And those gases. And we feel that, okay? So you'll see that question at some point next week, maybe Tuesday. Cameron. So this one. A drinking trough for horses is a right trapezoidal prism. Okay, right trapezoidal prism. With the following dimensions shown. It says it weighs, or wants to know how much it will weigh in regards to just the water. So we're not talking about, whether this trough is made out of wood or aluminum or whatever. We don't care about the weight of it empty. We care about just the weight of the water. Does that make sense? Okay. So I need to find volume. Okay. If I'm going to find a weight, got to find volume in this situation. So what are our bases here? Trapezoids. Okay. And they're a special type of trapezoid because that's 50, and so is that. It's isosceles. And the reason I need it to be isosceles is because that's 40, and it's going to allow me to draw in that altitude and that altitude, making this here what? 40. These are two triangles, and this is the importance of this being isosceles. These two triangles are what to one another now? They're congruent. Okay? So, how big does that have to be if this whole thing is said to be 100? 30. Okay? Now that's 30. That's 50. What does this have to be? It's got to be 40. It's a 3, 4, 5 triangle, isn't it? Okay. And a lot of times a 3, 4, 5 triangle is written as like 3x, 4x, 5x, or x could be any multiple of 3, 4, 5, right? So this is a multiple of 10. So that is H. This is B1. And our 100 here would be B2. Okay? And we need that because if you remember, base of a trapezoid, base area of a trapezoid is 1/2 the altitude, B1 plus B2. So that's going to give me the area for this base here. So go 1/2. H is 40. B1 plus B2 would be 140, right? That's 20. 20 times 14. Or 2 times 14 would be 28. Okay, so then I have 28,000 centimeters squared as my B value. Is everybody all right with that? Is that correct? 22 times 14, 28, 3 zeros, right? All right, so now I got to find volume. Volume of a prism is B times H, right? Well, B is currently this number. Now, what is H going to be? $200. Why I did something wrong here. I put too many zeros. B1 plus B2 is 100 plus 40, right? That's kind of why I stumbled through this. I think it should be 3 zeros. All right. Is that all right with everybody? All right. So this was centimeters squared. So this, we had to change this to centimeters as well. That's why we changed it to 200. Now when I multiply that out, 28 times 2 is 56. And then I've got 4 total zeros, right? That I have to add on beyond the... Why do I keep doing that? 28 times 2 is 56, and then the 4 zeros. 2, 3, 4. I don't know why I wanted to add a fifth one again. So that is centimeters to what power? Third. Because this was an area, it was centimeters squared, right? This was a distance with centimeters to the first. When I multiply like base, they add the exponents. So now centimeters cubed. Now, my question at hand says, I'm interested in a weight here, and weight is in regards to, or the conversion in regards to 1 cubic meter. Okay? So what we're going to do here is try to convert this into cubic meters. So if I use King Henry died by drinking chocolate milk, okay, and right now we are at that, right? We're at the centimeter sliding or starting point. And we want to slide our way over to meters, don't we? Okay, how many spots did I just move? 2, right? Okay. So how many spots do I really need to move? We move 6. Okay, we take as many spots we move in the slider times whatever that exponent, because that tells us all dimensions. Okay, left and right dimension, an up and down dimension, and a depth dimension, or forwards and backwards. All those get a decimal place if we move 2 spots. And that gives me 0.56 meters cubed. Okay. Now it says 1 meter cubed equals 1 metric ton. Well, at 0.56 meters cubed, isn't that 0.56 metric tons? A 1-to-1 relationship there, right? For every 1 meter cubed, you have 1 metric ton. A meter cubed, guys, kind of give you a visual here. These are meter sticks. Okay? So there would be kind of the base of your, that would be the base of like a cube aquarium. That's going to be 1 meter by 1 meter, and then this would be the height of it, right? So you visualize having that cube on your desk, filling it with water, it would weigh a metric ton. Okay? If you, anybody, you've seen like the scoop on a bobcat, right? Like a skid loader or something like that. You know what I'm talking about?
Yeah.
Okay, forklift type thing. But the scoop on those is 1 cubic yard. Okay, so we'll hold 1 cubic yard approximately, which 1 cubic yard is a little bit smaller than 1 cubic meter, for the fact that a meter has 3 more inches in it than a yard does approximately. But if you can visualize a scoop on a Bobcat, something you're familiar with maybe, that shows you then the amount of water that we're talking about when we say 1 cubic meter of water weighs 1 metric ton. So that's not, I mean, that's not a lot of water, is it? Okay, but it has a pretty good amount of weight on it. Questions on that? Is this something we can do? There are other ways of approaching this. Can we have changed everything from centimeters to meters and then work that way? Anybody do that? That's perfectly fine. Okay. We could do the work that we did by changing 2 meters to 200 centimeters, and then take our 1 meter cube of water weighs 1 metric ton, and actually convert that into seeing, okay, how much does 1 cubic centimeter of water weigh? And then multiply that number by the 56,000 number that we have, I think, 560,000 number. There are different approaches. But you still have to do the same types of conversions, the same amount of conversions, regardless of the approach you take. Does that make sense? All right, I like this question, and you're going to see something again like this next week, probably Tuesday, Cameron. It says a soda can has a diameter of 10.16 centimeters and a height of 8.89 centimeters. Right there, does that give me enough information to find the volume of this can? Volume is pi r squared h, right, for a cylinder? So we go pi. Radius, what's your radius? 5.08. And then the height is 8.89, right? I multiply that out, I get 1 can to be 720, got it here, 720.7407 cubic centimeters, right? Okay, but I want a 6-pack, right? So what do I need to do with that number? Times it by 6, and that will turn into 4324.44 cubic centimeters. Is that all right, everybody? Okay. The next question is, with the same 6-pack of soda, so we're going to stack 2 of these 6-packs. All right, and then we're going to take some cardboard and press that cardboard up against the sides of my can to create a box, a prism, that has the smallest possible volume. Okay? So the idea here is that our box is going to be tangent to all of these cans. Okay? So the obviously yellow cans is 1 6-pack, green one's second 6-pack, right? Okay? If I look straight down, okay, you're starting to see maybe the lengths and widths of our box, right? What would, kind of maybe in words, what would you describe that length as? Yeah, 3 times your diameter, right? Okay, so it's going to be 3 times, our diameter was 10.16. Okay, this here is going to be 2 times your diameter, right? So that's going to be 2 times 10.16. So there's your L. Maybe that's W. Now we got to look at it from this view, and we got to find this H. Okay? Well, how many cans is that? 2 cans, right? So that third dimension, your H, is going to be 2 times your altitude of your can, which ends up being 2 times the 8.89. So I'll take that number, I'll take that number, and I'll take that number, and there are my L, W, and H, and I'll multiply those, and that gives me the volume. Gives me the volume of that box to be 11012.1071 cubic centimeters. Is that all right with everybody? Okay. So I want to show you that box real quick. Okay. So we're looking at that box. Okay. It's got a volume of that 11012. Okay. Would you guys agree that inside that box there are some volumes that are being wasted? Okay. So for instance, and it's kind of hard to look at, I think, but I draw your attention to maybe that region right there. Okay? And now you think about that as a three-dimensional shape. Does that go all the way through that box? All the way through those cans, right? So that, 3D shape, if I were to pull it out, would maybe look something like that, where these are curved surfaces, right? Okay, that's wasted volume when I package these cans in this container, right? Okay, think about when you guys go buy, 12-pack can, 24-pack can, whatever, or cans of pop, and when you buy those, there is wasted volume in it. Okay, meaning that those cans came from somewhere, right? Those boxes came from somewhere, and they came from somewhere on the back of a semi-truck, right? And there's a lot of wasted volume inside that semi-truck now. There's a lot of space that could have been maybe replaced with product instead of just the air. So Pepsi or 7-Up or whoever is sending these products is paying to ship air. Does that make sense? Okay, which maybe some companies are not interested in do that. Okay, if you look at like Hi-C, doesn't Hi-C come in those little juice boxes? Those juice boxes are prisms, right? And they fit together pretty snugly, right? And there's no wasted space. Okay. Well, there's no when I'm shipping those, there's no volume that I'm shipping that is just vacant. Okay. I want to know how much of this vacant space, how much of this wasted volume there is. Okay? So how can I find that wasted space or that wasted volume? Is I'm going to take the volume of the box, which was 11012.107. And then I'll find the volume of my 12 cans. Well, I already know the volume of 6 cans, right? So the volume of 12 cans would be that times 2, so 8648.8862. That's the volume of 12 cans. Basically, take that 720 number we talked about earlier as the volume of 1 can and multiply it by 12. Okay? What can I do with those two numbers to determine the wasted volume? Subtract. Okay? So when I subtract them, I get 2. Let's see here. 236 volume that is wasted. 236 3.218 cubic centimeters. Okay? Which is the idea then, guys, is if I were to open all 12 of those cans, take them out of the box, fill the box up, it would be 2,363.218 cubic centimeters full of air. okay, or vacant, not having liquid. Does that make sense? Okay. It turns out to, if I take that number and divide it by 720, which is the volume of one can, it tells me that there is, in regards to wasted volume, it's about 3.5 cans, I think 3.29, so about 3.3 cans of product that could be added in. Does that make sense? Okay, so it's something to think about. And there are groups, you know, some large manufacturers. I'm assuming Pepsi probably has a math analysis department. That's somebody's job, or a group of people's job. They kind of do these calculations and analyze these things and decide that when we're going to maybe create new marketing, okay, maybe we create a new box or something like that. Is it really economical? Does it make sense to do that? Okay. Ford will have an analysis group. P&G will have an analysis group. All these big companies have math people crunching numbers and coming up with data to allow your CEOs, your executives, people to make decisions that have a reason behind them. Does that make sense? Okay. And often we're trying to save money when we're doing those things. Is that all right? Okay. I like that question, Kim. Or I like that a version of that question. Okay. I really like doing this. I like taking and putting maybe that in there. Okay. So that's a sphere, right? We're not talk about those yet. But if I put a sphere in there, does it start to look like maybe a bunch of tennis balls or racket balls, or how they're shipped, okay, or sold in the store? So we'll ask those types of questions maybe at some point. All right, let's get to, that was the last one, right? Awesome. For today.